Here is the counterintuitive truth about beamed power. The hard part is not making a beam. The hard part is proving end-to-end that the beam is safe, controllable, governable, and economical. As of 2006, short-range wireless power is already commercially mature. Inductive and resonant charging work, people trust them, standards exist. But that success does not translate to kilometer-scale power delivery. Far-field beamed power is still pre-commercial and highly application-specific. There are no verified grid-scale deployment figures in the available evidence base. The first high-impact insight is that physics forces your hand on architecture. In far-field systems, wavelength and aperture size set beam divergence. A beam that spreads too quickly wastes power and expands the area that must be controlled. So delivered power is not just about a stronger transmitter. It is about the geometry of the transmitting aperture, the receiver area, and how much of the beam the receiver can capture. That brings us to the second insight. Efficiency claims are meaningless unless they include the whole chain: generation, conditioning, the transmitting array, propagation through the medium, the receiving aperture, rectification, storage, and the final load interface. A classic mistake is to celebrate a great transmitter or a great receiver while ignoring everything between them. Without measured source-to-load efficiency, you do not have investable infrastructure evidence. You have a lab story. A third insight is that microwaves and optics trade problems. They do not remove them. Microwave beaming with rectennas remains the main lineage for far-field conversion efficiency and for space power concepts. Longer wavelengths make diffraction harder to beat, which pushes you toward larger apertures and larger receivers. Optical or laser power, with its shorter wavelength, can reduce diffraction for a given aperture. Yet it becomes more sensitive to atmospheric absorption and scattering, and much more sensitive to pointing errors. Safety constraints also tighten quickly, especially around eye and skin exposure. So control becomes the center of the whole enterprise. Optical wireless power transmission is, in many ways, a control and beam quality problem disguised as an energy problem. One active approach is retrodirective optical energy transmission using optical phase conjugation. The idea is to keep the beam aligned by using the receiver relationship itself to stabilize pointing. Even then, alignment is not enough. You need fail-safe behavior under occlusion, under disturbance, and under spoofing attempts. A credible system must shut down fast when the authorized receiver is not confidently locked. Next is the issue that surprises many energy planners. The medium is not just a passive channel. At high intensities, beam-medium interaction can become the limiting design variable. Modeling work has treated beam-induced plasma as a real constraint, not a curiosity. Under certain combinations of power density, frequency, humidity, and altitude, the propagation physics can turn into a safety and reliability problem. In practice, that means serious beamed power pilots may need environmental telemetry and automated shutdown as first-class subsystems. Another key finding is about where early markets are most plausible. The strongest case is not retail, public area beamed electricity. The stronger case is controlled corridors with fixed or semi-fixed receivers, where authorization is explicit and shutdown is monitorable. Mobility-focused wireless power transfer is also a distinct design domain. Moving receivers bring intermittent alignment, variable capture efficiency, and fast-changing loads. That can matter for transportation, robotics, aerial platforms, and space logistics, but only if tracking and authorization are robust. If you want to understand why this remains niche, look at what has been considered milestones in the peer-reviewed record. Orbit-to-surface beamed power for Mars base expansion was analyzed as far back as 1989. Microwave power transmission for space applications was synthesized in 1992, with rectennas at the center of the system framing. By 2000, researchers were already treating microwave beamed power conversion as a system-level problem. In 2004, Mars exploration concepts emphasized that architecture matters as much as components. Then, in 2009, policy work put safety, liability, public acceptance, and regulation inside the deployment problem. In other words, the field has been warning us for decades that governance is not an afterthought. That leads to the most strategic takeaway for capital allocation. Beamed power is not energy without infrastructure. It is energy infrastructure shifted into apertures, receivers, beam control, sensing, licensing, and exclusion zone management. So the near-term leadership move is not to bet on sweeping grid replacement. The near-term move is to fund measurement first, instrumented testbeds, demand complete efficiency accounting, demand measured shutoff latency, demand propagation monitoring, demand auditable safety cases, and clear liability allocation. Space-linked concepts remain compelling, but they are still about stacks of dependencies.